Here we have a problem about kinetic energy of electric charges. So we have two charges, Q1 positive and Q2 negative. These charges are held in place at a separation of 0.2 meters. If we release Q2, Q2 will move towards Q1, and we want to know what will Q2's speed be when it reaches a distance of 0.01 meters from charge Q1. And we have values for the charges and values for the masses of each object. As always, we'll start with a picture. So at the start of the problem, Q1 positive, Q2 negative, neither charge is moving, and they are separated by a distance of 0.2 meters. At the end of the problem, Q1 and Q2 are much closer. They are separated by 0.01 meters. Q1 is still at rest. It's still being held in place, but Q2 now has an unknown speed that we are trying to figure out. This is a conservation of energy problem. Notice that we cannot use F equals ma on this problem because the force that Q1 exerts on Q2 is constantly changing. As Q2 gets closer to Q1, that force that Q2 experiences gets stronger and stronger, and we can't deal with changing forces without doing some calculus. So instead, we'll use conservation of energy. So the initial potential energy of the charges plus each of their initial kinetic energies should equal the final potential energy of the charges plus each of their final kinetic energies. At the start of the problem, we can write the potential energy as charge Q2 times the voltage due to Q1 at their separation di. Neither charge is moving, so there's no kinetic energy of either charge at the start of the problem. At the end of the problem, there is a different potential energy. It's still Q2 times the voltage due to Q1, but now it's that voltage at the new separation dF. Q1 is still at rest, so Q1 has no kinetic energy, and Q2 has a kinetic energy that will depend on the speed, which we are trying to figure out. So our kinetic energy equation, our conservation of energy equation, when we plug in what we found on the last slide, we have initial and final potential energies and a final kinetic energy for charge 2. I can plug in my equation for the electric potential due to a point charge, kq1 over distance, where that distance is either di at the start of the problem or df at the end. If I now plug in all the values I know, m2, k, q1, df, q2, di, I can get a numerical equation. I can easily solve this for V2, and I come up with 28.41 meters per second. That will be the speed of charge Q2 when it is 0.01 meters away from charge 1. And it's easy enough to take this value for V2 final, plug it back in here, and just make sure it works. That's the end of our problem. We had a charge that moved through some change in electric potential. Due to that, the charge gained some kinetic energy, and we figured out the speed associated with that kinetic energy. I'll close with a question for you to think about. If instead of releasing just Q2, what if we had released both charges so that they were both free to move? In that case, would the final speed of Q2 be larger, smaller, or the same as the value we just calculated? You should be able to think about this conceptually and answer this question without doing any calculations.